Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing, and for rest we are here to talk. So we were following our pattern wise DSA sheet. In this we were doing tree topic and the pattern was BFS traversal. In the previous video we have solved this problem, which is top view of a binary tree, and in this video we'll solve the bottom view of the binary tree. Remember, the prerequisite of this problem is the top view. So if you have not watched that previous video, this video will not be easy for you. So if you have watched the top view of a binary tree, then we will discuss the bottom view of the binary tree. So bottom view is nothing but when you are visualizing the tree from the bottom side, what are all nodes visible to you, that we will print. Okay, talking about the constraint is similar to what we had in our top view of a binary tree. Okay, so let's come here. So this is a tree we have. So if you see from the bottom side, what are all nodes will be visible? Can I say 4? Yes. 5 will be visible or not? Yes, 5 will be visible. 4 will also be visible. But as per this, we have to consider 4 and not 5. Why? Because if you see here in the example number, this example, see 5 is visible. Okay, 3 and 4 are on the same vertex level. Correct? So if they are on the same vertex level, means 3 and 4 both will have 0, 0 as vertex. So in the answer you can see 4 is visible, not 3. Okay, so you have to consider the next one. Okay. Now this 4, then this 5 will be visible. Yes. 6 will be visible. Yes. And this 3 will be visible. Yes, of course. Why not? Because vertex is 0, 1, minus 1, minus 2, then again minus 1, then for this 0, correct? For this minus 1, for this 1, for this 2, and for this 1. Okay. So definitely for minus 2 we will have 4. Correct? For minus 1 we had 5 but overridden, so 4. Correct? For 0 we will have 3. For 1 we will have 5. For 2 we will have 6. Correct? This 9 and this 1 will not be visible. So this is what we are expected to print. Okay. So in the top view of a binary tree, what we did, we initialized the vertex. Correct? But remember, with BFS we need not to check for the levels, because in BFS by default we are traversing level wise only. So we just have to take care about the root value, node value and the vertex. Correct? So this is a vertex we have. Now for the next one minus 1 and for the next one plus 1. So what we will do now, in the map for 0, if it is not there, definitely we will add. What we did previously, if the 0 is not there, so whatever is the first element, that will be our top view. If at 0 again we are encountering any other variable, okay, then that we will not update, because that will not be the top view. But as this is bottom view, so if for 0 you have find, you update this 1. Okay, now again for 3 you have find, so override this 1 with 3, because we have to check for the bottom. So whatever, like level wise when we are traversing, definitely we are going downwards, and if in downward direction or downward level, if you have found any other node for the same vertex, then definitely that downwards node will be visible. So it is very important to update it. Okay, now for minus 1 also we will update 2. Now for minus 2 we will update 4. Now for this is level order, right? So in level order what we will do, for plus 1 we will update 9. Why? Because you have to update like this. Okay, now for minus 2 we will update 4. Okay, and this will be what? 0. Again for 0 we already have, so we will update this with 3, because we have to check for the bottom view. Okay, now what we will do, again we will go for level order, which is obviously minus 1 for this. So for minus 1 we already have 5, so we will update. Correct? Now 3 children, which is minus 1 and 1. Again for minus 1 we have 4, so we will update. Now for 1 we have 5, so 9 we will override and 5 we will update. Now this is 2, so for 2 we have no element, so 6. So at the end 3, 4, 5, 4 and 6. Correct? Yes. So if we will print for minus 2, minus 1, so for minus 2, like for minus 2 we have 4, okay, for minus 1 we have 4, okay, for plus 1 we have 5, okay, for 0, first 0 we have 3, for plus 1 we have 5, and for plus 2 we have 6. So this will be the bottom view. See, 4, 4, 3, 5, 6. Correct? So if you have watched the previous video, top view, again I am saying, because discussing it again will simply waste our time. So if you have watched that, there we have written the code. What we have written in the code, ki if that particular vertex, okay, if that particular vertex in our map, like map does not contains that vertex or HD, horizontal distance, if it does not contains that vertex, so what we did in the answer, like in the map, we have put in map for that HD, we have put root dot value. Remember? Yes, we have inserted this, but we have to override. Why you are looking for key if that vertex is there or not? Simply keep putting it, don't check it. If you will keep putting it, first you will put 1, then you will put 3, then you will put something else. Basically you are overriding it. So basically we are checking for the bottom level of nodes for the bottom view. Okay, so the only line of code you have to change is just remove this code. Okay, so what we'll do, we'll go in the top view, we'll copy the whole code, and we'll go in the bottom view and we'll just paste it. As the like function name was bottom view, so we will write bottom view. Now rest all will be same. We will create pair because queue in Java does not cannot store 2 values at a time, correct? So that is why pair is needed. Now what we'll do, we will create the array list as it is, we'll create the map, we'll create the queue. In the queue we'll insert the first pair with the node which is root basically, and the vertex which is 0. Now until the queue is empty, we'll pop the node. Okay, and now here we were checking na, ki if it is not there, then only insert. If second time you are getting the same vertex, then don't insert that node. Why? Because whatever in the level wise, for the top view, for any vertex, if you are finding the nodes again, means for sure those nodes are downwards, so that will not be visible from the top side. But in the bottom view, whatever at the same vertex at different levels going downwards, if you are finding another node, means for sure that will be visible na. See, first 1, then again you found 3, so for sure from the downward, this downwards level vertex is needed, this node is needed, correct, not 1. So we'll keep on overriding. So this only if code will need to get removed, and rest other will be as it is. Okay, so let's run the code. Here we are actually inserting the like roots left child and right child in our queue. Now let's submit this. So the time and space complexity will be linear O of n, because for every node we are traversing, correct. Similarly, here is the code for C++. So if you have understood top view, and then definitely you can do bottom view on your own. And here is the code in Python if you are from Python background. Now for the DFS code, what we have to do. In BFS though, we cannot store like vertex, so we need to create pair. But in DFS, no matter how many variables we need, in the function call itself, along with the root, we will send what? Vertex. But in breadth first search, level was by default maintained by the queue, but here level is not maintained, so we have to send a level variable also. Remember in the top view how we did? First the base case required, ki if root is null, simply return, don't do anything, simply return. Now what we did, see, initially we have this root, level 0 and vertex also 0. So can I say in the map, with the help of this vertex 0, I'll insert this 1? Yes. But as we have map, and in BFS, so for any vertex we just have inserted the node and overwritten, because level was maintained. But here level we don't know, so in the function only we have sent. So it is very important to store the array list of 2 sides, where we will insert the node first, which is 1, and the level later. Okay, so if this vertex is not present in the map, our task is to create the new integer array of size 2 and insert it, correct. So hence it is very important to check ki if our map does not contains what, this HD, then what we will do, in our map we will put with this HD, what we will put, new integer array, and what will insert, root dot value and that level. Understood? But here too we have inserted 1. Now we'll go for left child and right child. So what we will do, we will call the DFS function with root dot left. Very good. Now HD will be -1 because we are going towards left side, so vertex will be -1, and level will be +1 as we are going towards downside. Similarly DFS root dot right HD will be plus 1 because we are going towards the right side, and level will be plus 1 because we are going towards downward. Correct? Now what we will do? See, here 0 has been inserted. Okay, 0 level and 0 vertex. Now here 1 level and minus 1 vertex. So similarly for minus 1, what we will insert? Root and level. Now 2 level and minus 2 vertex. So can I say minus 2? For minus 2, the vertex node will be 4, yes, and level will be 2. Why level is required now? We'll see this. Now we'll go for 5, correct? So level 3 and vertex minus 1. So level 3 but vertex minus 1. So if what will say, ki, is this vertex already present? So here we have written ki if not present then only insert. Yes, if not present then insert this root value and level. What we did. But what if it is present? For 5, listen it very carefully. For 5, we'll check minus 1 is already there. But we have to override. How we can override? Think again. How we can override? So can I say ki for minus 1 override this 5. Override this 5. So how we can override this 5? You can say ki okay, simply override now. Okay, we'll override. The next time simply override. Okay, we'll override 4. Okay. But you know what? Here to you know ki 5 has been occurred at depth level. Correct? At depth level. But what will happen? For this the index is 1. Remember? For this index is 0, for this index is 1. But as you are doing the depth wise search, so you will be at 1, then 2, like this, 5 first before 9. So for 5 you will insert, like for one index you will insert 5, remember? Then later on when you will return back, you will come at 9 and you will say, hey, for 1 it is already there, so you will say no, override. So you will override 9, but 5 was visible now from the bottom side, not 9. So hence the level comparison is also important along with insertion of node. So instead of simply checking ki if it is not present, put, even if it is present, don't override. You first need to check ki whatever you have encountered now, is it like the level of the current node is greater than previous one, equal to also. Why? Because when you will check later 4, so 4 will say yes, it is not greater than, but still you have to override 4, right? So if what we will write ki if level, which is current level, is greater than equal to what? Is greater than equal to the level present in map. So what we'll do? Map dot get for that HD, correct? But index 1, because one index is actually having the level. So if the current level of 5, which is 3, is greater than the previous level, which was 1, then only override. So 9 will get, 5 will get overridden, correct? For minus 2, for minus 1, sorry, for minus 1, 5 will get overridden with level 3. Now what will happen? We'll go on return back, and then we'll go on 3. So for 3, the vertex is 0. Now for 0, you will say ki earlier we already have 1. But we'll check the level. The level is 2. Earlier level was 0. Definitely it is greater. Yes. So we will override. So we'll override and make it 3 with level 2. Correct. Now we'll go at child 4. For 4, the index is minus 1, level is 3. Correct. Yes. So again here we will check for minus 1 we already have. But is it like the level is greater than equal to? Because of equal to, we will override this with 4. So again this will get overridden with 4 and level 3. Now we'll go towards the 3's right child, which is 5. So vertex will be 1 but level will be 3. So for 1 we have nothing. So for 1 we will update 5 with level 3. Similarly for 6 we have nothing. So we will insert for 2 we have 6 with level 4. Now what will happen? We'll return back, we'll return back, we'll return back, we will return back, and now we'll go at 9. For 9 the level is 1 but the vertex is also 1. So here you will say ki hey, vertex is 1. So okay, wait, don't override. Check the level. So level is 1. Earlier the level was 3. So whatever we have encountered now is present towards the upside. And definitely if we will look from the downside, 5 will be visible, not 9. So don't override. So that is why this condition is very required. So in top view it was less than, and in bottom view it will just like we just have to change the sign and whole code will remain same. So here is the code. First we'll create the map, and then in the bottom view what we are doing, we are calling the DFS function and we are filling this map. and at the end we'll create the answer, and from the map values we will read the first value because we are inserting the integer array. So first value represent the root value and second was level, and at the end we'll return. And in the DFS call what we are doing, we are checking if the root is null, return, and then we are checking ki what if the map does not contain. So if the map does not contain any element, no need to check for the level, simply like create the new index with the new integer array. Now if the map contains, then we have to only insert if the current level is greater, okay, because it is bottom view. And now these two calls are just for the left side call and the right side call. For left and right, definitely the vertex will change, which is hd minus 1 and hd plus 1, but level will increase for both left and right child. So now let's run the code. Again, the only line of code change which we did was just we changed this sign compared to the top view. So that is why I said ki prerequisite of this video is the top view. So done. So this is your bottom view code in Java for DFS. Here is your code in C++ and here is your code in Python if you're from Python background. So if you understood the bottom view of a binary tree, both with the DFS and BFS, and what was the code change compared to the top view, then definitely you are eligible to go in the sheet and mark the next question, which is bottom view of a binary tree, as done. So I hope you all understood and you have submitted the code on your own. Along with that, you are also preparing your notes because that is very important when you have to revise it. So with the hope that you all have understood, and you will definitely hit the like button and subscribe the channel if not yet subscribed. I will attach the link of the sheet and my social media in the description. If you need any guidance, do reach out to me. And that's it for this video. Let's meet in another video with some more interesting questions, topics and patterns. So then keep learning, take care of yourself and your family.